А теперь? Ну, вроде нормальный звук, как обычно. Так. Здравствуйте. Okay, so we're going to discuss section 6.2, primary modules and ideals. So definition, I separate this definition into two parts. So first about a module, second is just a special case of ideals. So a submodule, so submodule n inside some given module m is called primary, or if you want to be more specific, you add p primary. So this P stands for some prime ideal. If you look at the associated primes of the quotient,
P in parentheses.
So this is a prime ideal. So
Yeah, we put it in parentheses to emphasize that it is.
let me just finish the definition. So if this set of associated primes has just one point, namely point P. So if you just want to say that the quotient has only one associated prime and you don't worry what prime it is actually, you can say this is primary. But if it is important what prime ideal you consider, you say this is P primary with respect to this prime ideal. So this contains a little bit more information. It contains exactly what prime ideal you have here.
Just ask about notation. Do we put parentheses about
No, this parenthesis just means that this is kind of additional information. So it's what in parentheses you can just skip. So maybe it would be better if I just write something like this. So this is part of notation that could be skipped. So this is a primary submodule, and of course, second part, an ideal I inside the ring R is primary. Again, I can do the same thing and say this is P primary, but let's for shortness say it's primary. Of course, if it is primary as a submodule. It is primary. So I want to say that this theory of primary modules, primary decompositions, started with ideals. So initially, people first defined what's a primary ideal and then generalized this to primary modules. So you can see in this sense for modules, this definition may be not completely kind of what you would expect. I think you would expect to say that module kind of has a simple structure if the set of associated primes of the module contains only one element. Here this is for the quotient. So this is because we're mostly interested in the primary ideals, and this is kind of as a submodules of the ring. So there's also another terminology. You call a module coprimary if the set of associated primes is just one element P. But we're not going to use this terminology. Okay, so first proposition. Again, maybe it makes sense to separate this into two parts for modules and ideals. So a submodule, so this is the first part, a submodule n in the, so of a Noetherian modulo M. So in this chapter is essentially about Noetherian rings and modules. So I always need to assume that something is Noetherian. So if a submodule of a Noetherian module M is primary, if and only if the set of zero divisors for the quotient module is the same as the radical of the annihilator of the quotients. And the second part, an ideal Q. So there is again the standard convention as for maximal ideals you use little m, for prime ideals you use little p, for primary ideals you usually use little q with indices. So an ideal Q in R is primary if and only if every zero divisor of the quotient ring is nilpotent. So if you take some elementary textbook where there are no theory of associated primes, this can be used as a definition. Right, so this is kind of close to the definition of the prime ideal. For a prime ideal, you don't have any zero divisors. Here, if you have zero divisors in the quotient, then these zero divisors are exactly nilpotents. And also there is a kind of second sentence in the second part. The radical of a primary ideal is prime. Okay, so let's prove this. The proof is actually very simple if you just remember the following property, that if you want to compute the radical of the annihilator, well, in this case the quotient modulo M modulo N, we know that we can compute this as an intersection over all prime ideals associated to this module, so in this case M modulo N. So this is one thing that we already know from the previous lecture. And the second thing that we also know, that the set of zero divisors on a module, so again in this case module is the quotient, this is the same thing as the union over the same set of prime ideals associated to the quotient module. So these two things we already know. But if you know this thing, I think this is immediately clear. Right, so this first part, because, well, you're comparing, if you have a finite set with more than one element, then this intersection is smaller than this one element, and this union is larger than this one element, so they can't coincide. So they can coincide if and only if the set of associated primes is just one element P. So these two things together immediately imply part one. But part two is just again special case when you consider module M to be a ring and module N to be ideal Q. So in this case, this statement is just saying that the zero divisors of the quotient ring are precisely the nilpotents of the quotient ring. So one immediately implies two. Well, I would say two first part. And well, the second part is also easy, right? So this is because if you want to compute the radical of a primary ideal, well, what we need to do, the radical of Q is again just the intersection of all associated primes, but in this case there is only one associated prime, so this is just P. So this proof is really easy. So next proposition, which is also quite elementary. So let's take N to be a submodule of an Noetherian module M. So then ideal annihilator of the quotient is primary. Of course, primary as ideal. So proof. So let's for shortness say that the ideal I is the annihilator of the quotient. Now suppose I have two elements, A and B, in the ring such that the product belongs to the ideal I. So product annihilates the quotient module M module N. And let's assume that, for example, B is not an I. So in other words, well, I can say that A is a zero divisor for the quotient ring, right? So I want to show that this I is a primary ideal, so I take A being a zero divisor in this quotient ring, and I want to show that this A is actually nilpotent. Well, but it can be done in just one observation. So if you consider A, well, we can't claim that this is also in the annihilator, but at least we can claim that this is a zero divisor on the quotient module. Right? So that's a zero divisor. Well, I think it's clear more or less, right? Because, well, it annihilates, AB annihilates everything, so you take an element with some representative little m, consider Bm, so A annihilates this element with representative Bm. And this we can also compute by the previous proposition as the radical of the annihilator. So in this case, this is notation for the annihilator is I. Now that's what I want. This is the end of the proof. Right, so I take a zero divisor, say zero divisor in the quotient R modulo I, and by this computation I can see that this is actually nilpotent. Okay, just a short remark. The converse to this proposition fails in general. So you cannot say that the submodule is a primary submodule if you only look at the annihilators. And an example is the following. You take R to be a Noetherian ring. Take two prime ideals such that P sits in Q. So these are primes. And module M is just a free module of rank 2. And the submodule N is the sum of these two ideals. So what we can say about the annihilator of the M modulo N? So what's the annihilator in this case? Yeah, so in this case the annihilator is just ideal P, but what we can say about the associated primes of the quotient? And also, of course, this quotient is just R modulo P plus R modulo Q. Yep. So in this case, we see that the annihilator is not just primary, it is prime, but the submodule is not a primary submodule since the quotient has two associated primes. So the converse is not true in general. Okay, now let's do several examples. So the first example is kind of quite elementary. So you take R to be a principal ideal domain. So it's elementary, but it gives some, at least some intuition about this primary ideal. So let's take a primary principal ideal domain, and let's take an irreducible element. Maybe not to confuse this with ideals. So let's say X in the R is irreducible. So that's an irreducible element. So then we know that principal ideal generated by this element is prime ideal. But if you consider ideals generated by the powers of this element, these are primary ideals. So these give us some examples of primary ideals which are not prime ideals. Of course, any prime ideal is a primary. Okay. Second example, I want to consider Q, which is an ideal generated by the x and y squared inside the polynomial ring on two variables x and y.
So do you assume in the previous question that n is primary or no?
N?
In the previous, do you assume that n is primary?
Yes. Sorry. Well,
It's not written there.
it's sorry. I just forgot to write this. Of course, this is a primary submodule. This is primary submodule of an Arthurian module. Yes, definitely. So the idea is if you consider primary submodule, consider annihilator, then this is a primary ideal, but the converse is not true. Okay. So I claim that this ideal is primary. Is it clear that this is primary ideal? Yeah, for example, we can take quotient, and in the quotient it will be a polynomial, say in y, modulo y squared. So there is a zero divisor y, but this y is also important. So that's a primary ideal. So then I want to compute the radical of this ideal. So what's the radical of Q? Yes, so the radical is the maximal ideal generated by the x and y. Well, we know this is primary ideal, so there is a unique prime ideal containing this, and it's quite clear that this ideal is containing this Q, but there are no more other ideals. Okay, so let me maybe fix notation, and let's say this is M. So then I can see that M squared is contained in the Q, and Q is strictly contained in the M. So what's interesting about this example, so we constructed a primary ideal which is not a power of a prime ideal. So Q is not a power of a prime ideal. So in example 1, every primary ideal is just the power of a prime ideal, but even if you take polynomial ring with two variables, that is not true. Okay, example 3. So in this example, I take ring R to be a quotient of the polynomial ring in three variables by the ideal xy minus z squared. So then I consider ideal P in this quotient. This will be generated by the classes of x and z. So clearly this is prime, right? Why this is prime? So what's the quotient of the R by this P? Yes, so that's a domain, polynomial ring in one variable. So that's a prime ideal. So this is prime, but I claim that the power of this prime ideal is not primary. So in example 2 we see that there are primary ideals which are not powers of prime ideals. In example 3 we're going to see that powers of prime ideals are not necessarily primary. Okay, so why this is not primary? Well, we have product of the x bar and y bar. Well, since this is the same thing as the z bar squared, this belongs, and z belongs to the P, so this belongs to the prime, to the ideal P. Sorry, even more is true. This belongs to the ideal P squared. Right? Now, what we have here is definitely x bar is not in the P squared. Okay, so then if I consider y bar, then I claim that this is not in the radical of the P squared, which is again, we know that the radical of any power of any prime ideal is the same ideal P. So I claim that y bar is not in the P, which again is quite clear by the definition of P. So this is true. So P squared is not primary. And this is the proof of this. 4. Now we consider ideal I generated by the x squared.
So we prove this, we prove that it's not primary. We want to prove that our quotient is P squared is not.
Well, we're showing, so if you look at this product in the quotient modulo P, we're going to see, well, we see that this is a zero divisor, modulo P squared.
Yeah.
So this is a zero divisor, since this is not a zero in the quotient.
Yeah.
So, and since we don't have this inclusion, this is not a nilpotent. So that's a zero divisor, which is not a nilpotent in the R modulo P squared. Okay, so consider ideal again generated by the two elements x squared and xy in the ring kxy. So I claim this is not primary. Well, again, in the quotient, if you take the quotient, you have zero divisors y, which is not an nilpotent element, the class of y. So that's not a primary ideal. But what's the radical of the ideal I? Can you find the radical? Yeah, that is right. Just this ideal x. You can do this by a direct computation. So clearly, this ideal sits inside the radical, and if you take anything in the radical, it will be proportional to the x. So in this case, we see that we have an ideal which is not primary, but the radical of this ideal is still a prime ideal. So the upshot of all these examples, or all these stories, that you need to be accurate with the primary ideals. You can use the definition, or the two definitions with the associated primes and the nilpotents, which are zero divisors. But you can kind of use any other conditions, like radical is a prime ideal, this is false. And you cannot say that this is necessarily power of some prime ideal, it's also false. So this is why we're doing these examples. But it is a little bit nicer when we consider not just prime ideals, but maximal ideals. So in the next proposition, we have the following two observations. So first of all, M is Noetherian module. So then the annihilator, so the radical of the annihilator of this module is a maximal ideal. So M is an element in the spec M of R. If and only if the set of the associated primes of M consists of one element, namely this maximal ideal. So if you know that we work only with the maximal ideals, then actually these two conditions are equivalent, which is not true for prime ideals. And the part 2 of this proposition, so if an ideal Q is contained in unique prime and Qm is not equal to M, so Qm is some submodule. If we let's assume that this submodule is not equal to the module, then Qm is primary. So in particular, we get several examples of some examples of primary submodules by considering powers of the maximal ideals. So take a power of maximal ideal and consider the corresponding submodule. Of course, in this case, we still need to assume that this is not the whole module M, so it has to be strictly smaller. Well, proof of the first part. So in one direction, so let's assume that the set of the associated primes, so here we know that the set of the associated primes of the M has only one maximal ideal M. Well, then we immediately can see that the radical of the annihilator of M, well, this is just the same maximal ideal M. Despite the general property, but you can, for example, imagine that the submodule you consider N, this is just a zero submodule. And we know that in general it will be intersection of all associated primes. Here, only one element, so the answer is immediately M. So in one direction this is clear. Now in the other direction, suppose we have P, which is associated with the module M. So then, well, clearly annihilator of the M is contained in any associated prime. Well, annihilator annihilates everything, and this P annihilates, well, some elements. So then, if I know that the radical of the annihilator is M, I can do the following computation. So M, which is the radical of the annihilator, this is contained in the radical of the prime ideal P, but the radical of prime ideal P is exactly prime ideal P. So maximal ideal M is contained in some prime ideal P. So by maximality, they has to coincide. So in other words, whenever you consider an associated prime, this associated prime is necessarily this maximal ideal M. So this gives us direction in the like this. If this is true, then the set of the associated primes is just one element M. So second part, if an ideal is contained in a unique prime, well, everything follows immediately if you just notice that this unique prime has to be maximal ideal. Because any ideal has to be contained in a maximal ideal, which is already prime, and this has to be unique. So the unique prime is automatically maximal. Okay, so this is this is contained in the maximal ideal. Now I know that Q is contained in the annihilator of the M modulo Qm. Well, this is doesn't require anything. This is just because of the definition of the quotient module. So hence any associated prime contains Q. Right, so and the rest of the proof is exactly the same. So in the annihilator we have Q, so it means that, again, as in the argument that we already have here, so any associated prime contains the annihilator, right? So then this contains Q, and since Q is contained in only unique maximal ideal, so any associated prime is this unique maximal ideal. Okay. Now let's just reformulate the statement for the maximal ideals. So here I assume that R is Noetherian ring. And Q in R is an ideal. So then the following are equivalent. So first condition, so Q is M primary and M is maximal. Second condition, the radical of Q is M. So conditions 1 and 2 are equivalent because we have this proposition. So this is just special case for n ideals. And for ideals you can also formulate third condition. There is n greater than 0 such that M to the n is contained, maybe coincide with the Q, and Q is contained in the maximal ideal M. And conditions 2 and 3 are equivalent because the ring is Noetherian, and we prove this for Noetherian rings in the very beginning of the course on the seminar.
What condition exists?
Exists some positive n such that M to this power is contained in the Q and Q is contained in the M. So Q sits between maximal ideal and some power of the maximal ideal. Okay. And the last proposition in this section. So let's take n in the M to be primary submodule. Of a Noetherian module M. And let's take S to be a multiplicative subset. So then we get the following three properties. So one, if the annihilator of the quotient M modulo n intersect S in a non-trivial way, so this is not an empty set, so then the localization of a primary submodule coincides with the localization of the module. second property, that if the annihilator of the quotient module intersect S in a trivial way, so this is an empty set. So in this case, localization S inverse n is primary in the localization of the module S inverse m. And 3, there is a bijection. So there is a bijection between primary submodules of M such that, well, we have condition 2, so such that annihilator of the quotient intersect this S is empty, and primary submodules of the localization. So I'm not going to prove this, I'm going to leave this as an exercise, but there are no really new ideas in the proof. This is, if you understand localizations and understand definition of a primary module, you can do this. Maybe we'll do this on the seminar.
So I have a question about the corollary here.
Mhm.
Wouldn't that mean that every primary deal and the theorem ring is maximal?
No.
I mean, for say put Q equal to P, the number 2 is satisfied, therefore P must be primary.
No, no. If Q is equal to some, if Q is equal to some prime ideal,
Yeah.
well, but then you cannot say this is maximal.
Oh, we could put M maximal like in the initial.
Yeah. So
initial case.
yeah. So everywhere here, M is a maximal ideal.
So it seems like it is number 1.
No, this is a M primary where M is maximal, a radical is some maximal ideal, and this is between two powers of a maximal ideal. So in all three conditions, M is maximal. So maybe I just separate this from the first condition and just say this is true in all three cases. M is maximal everywhere. Okay, so next section, primary decomposition. So now let me say that all modules are Noetherian. To save some time, let me assume that all the modules are Noetherian. So first we have the following quite elementary observation that we're going to use later. So let's take M1 and M2 inside M to be two submodules which are P primary. So M1 and M2 are P primary submodules for the same prime ideal P. So I assume that P works for M1 and it also works for M2. So then the intersection of M1 and M2 is P primary. Again, for the same prime ideal P. The proof is just combination of the ideas that you know very well. So you take M, consider the canonical map, which is the direct sum of two canonical surjections to the quotients. Right? So then this map, well, not necessarily surjective, but at least we can understand the kernel. So the kernel of this map is exactly the intersection of M1 and M2. So in other words, I can say that module, which is M quotient by the intersection, is a submodule in the direct sum of these two quotients. But we know in general that the set of the associated primes of a submodule is a subset of the associated primes of the module. So then we can say that the associated primes of the M modulo M1 intersect with M2 sits inside the set of the associated primes of the M modulo M1 union with the set of the associated primes of the M modulo M2. Right? Just by general property of the associated primes. We discussed this last time when we considered short exact sequence and the corresponding properties of the set of the associated primes. Here what we can say, well, I assume that M1 and M2 are two P primary submodules. So this is just a set that has one element P, and this is a set that has one element P. So necessarily this is just a set with one element P. So definition, a submodule N is called reducible if I can present this as an intersection of the N1 and N2. So here I want to assume that this Ni are not equal to the N. For I is equal 1 and 2. So this is actually an interesting intersection, not a trivial one. So this is called reducible, and otherwise submodule is called irreducible. Yes, not equal to N. So otherwise, N is called irreducible. Yeah, two submodules. If you can present a submodule as an intersection of two other submodules, then this is reducible. Otherwise, this is called irreducible submodule.
Everything is still Noetherian, right?
Yeah, everything is Noetherian. So of course, you can give a definition for any module, but you can develop reasonable theory only for Noetherian modules because you're going to need some associated primes to develop the theory. No. So irreducible modules, it's kind of, we're not really interested in irreducible modules. We're going to relate this notion of an irreducible module with a primary submodule. So for us, primary submodules are interesting submodules, and irreducible, like more or less technical step. And I also want to say that if you know some representation theory, for example, for finite groups, you probably know what an irreducible representation is. That's the same thing as irreducible module over the group algebra. This has nothing to do with it. The definition is completely different. So we're going to see at the end of the lecture why the terminology is with this irreducible. Because, well, think about ideals. Ideals are main examples. Irreducible submodules correspond to irreducible ideals correspond to irreducible varieties. So this is why we have this terminology.
Irreducible varieties in spectrum.
It's just
Yeah, in the spec, yes. irreducible subschemes of the spec, if you want precise terminology. Okay. So proposition. So any submodule, of course, here it's very important that the module is Noetherian. So every submodule n inside M where here this is intersection. So any submodule n can be presented as a finite intersection of irreducible submodules. So in some sense, you can say from this proposition that these are basic building blocks for all submodules, but the operation you build with is the intersection. So maybe not the standard operation. So you're probably used to when you, instead of as a main building operation, you use sum, but these two operations are related by the short exact sequence. And so for submodules, you need to use intersection if you want to use sum for the quotient modules. So this kind of maybe a little motivation behind this construction about the definition with the irreducible, with the intersection. Okay. The proof is the following. We take set S, so let S to be the set of all submodules with no such presentation. So we're going to assume that S is not empty and derive a contradiction. And if you can derive a contradiction, then we're done. Okay. So here M is an Noetherian module. So for this subset of modules, there is a maximal element. So let me say if this S is not empty, then there is maximal element. Let's say this may be N0. If N0 is irreducible, we get a contradiction, right? Because well, this N0 is just this presentation of N0, right? So this immediately gives a contradiction. So this N0 can be irreducible. So we need to say that N0 is necessarily intersection of the N1 and N2. Right? If we have such intersection, well, then definitely we can say, well, N1 and N0 is contained in the Ni, right, for I equal to 1 and 2. So these are two modules which are larger than N0. And N0 is a maximal element. So N1 and N2 are outside of this set S. And hence they have this presentation that we want as a finite intersection. So then N0 has such presentation. So this is I equal 1 and 2. Hence, and I is not in the S for I equal 1 or 2. So an I for I equal 1 and 2 are finite intersections of irreducibles, and hence n0 is a finite intersection of irreducibles. Definition. So essentially I'm going to fix some terminology. So a decomposition of a submodule n inside M is a presentation of this n as a finite intersection or some other proper submodules. Okay, so this is part one. There are going to be 4 parts of this definition. So this is just a decomposition. Any intersection, well, any finite intersection for any proper submodules. Oh, I'm saying proper submodules. So Ni is not equal to M.
And not equal to n.
Ah, yes, and not equal to N. Well, kind of in this general part, I can assume that they can be equal to N.
Okay.
So I'm going to add this condition later. So to avoid some trivial decompositions. So a decomposition is called irredundant неизбыточная. So the composition is irredundant if none of ni's can be omitted. So for example, answering to your question, in the first part I can still assume that maybe n1 is equal to n, but if I want a redundant decomposition, I can just remove this. Okay, so maybe what I'm saying is not correct. Probably what I need to say, maybe if n1 is equal to n2, I need to remove, say, for example, n1. But if n1 is just equal to n, maybe if I just remove first component, the rest of the intersection is not necessarily small enough, right? So it may be strictly containing and so on. I'll take this back, but what I want to say, for example, if n1 is equal to n2, I need to remove n1 and just start with n2. So the decompositions are irredundant if none can be omitted. So a decomposition is called irreducible if all ni's are irreducible. And in fact, we already proved the theorem that any module has an irreducible decomposition. So 4, a decomposition is called primary and this is what gives the name for this section, if all ni's are primary submodules. So the goal is, of course, to show that for any submodule you have a primary decomposition. Okay, so first, if we start with any decomposition, so if n is the intersection of some submodules, so we can group ni's such that all associated primes I need to say that this is not just any decomposition. I need to say that this is primary decomposition. So let me say that if we have such intersection and all these submodules are primary, meaning that associated primes of the n modulo ni, this has only one element pi. So this is a primary decomposition. So then we can group ni's such that all pi's are distinct. No, distinct, different. So what I'm doing here, I'm saying that, well, for example, I have n1 and n2. And associated primes, well, they have only one element, but p1 and p2 are the same. So then instead of considering n1 and n2, I consider the intersection. And I can do by the proposition that I proved in the beginning of this section. Intersection of two p primary submodules is again p primary. So that's what I'm doing here. I'm just grouping, if they have the same associated prime, I just group them together and consider as one p primary submodule.
Is finite always?
Yes, always finite, yes. We consider only finite intersections. Okay. Yeah, and there's also another terminology. So such decompositions, meaning all pi's are distinct, are called shortest or minimal. Okay, I think now we fixed. No, there's also a little bit of terminology. So, and in this case, ni's are called primary components of the submodule n. So now I think we fixed all the terminology. Yeah, in the shortest decomposition, these are called primary components. Okay, so now we kind of need to show that the main theorem that any submodule has a primary decomposition. Well, surprisingly enough, this is a complete triviality. So we have next proposition. An irreducible submodule is primary. So if we can prove this, we have a primary decomposition. Now, because we know that any submodule already has an irreducible decomposition, so this irreducible decomposition is actually primary decomposition. So let me just say in particular, any submodule has a primary decomposition. Okay, but we really need only to show that the first part is true. Okay. Let's take n inside M, which is irreducible. But not primary. You want to derive a contradiction. Well, first observation, just for convenience, by going to the quotient without loss of generality, we can assume that the module we consider is a zero module, so n is 0. Okay, and then there are two, so this is not primary, there are at least two prime ideals, P1 and P2, associated, well, if n is 0, I can just say that this is associated with the module M. So then it means that I can embed R modulo Pi, or some isomorphic copy of some submodule Li that sits inside M. And this is for I equal 1 and 2. So more precisely I can say that there are elements, more precisely I can say that the annihilator of the X is isomorphic, well, not just isomorphic, equal to the Pi for any X in the Li. Okay, so what if I take X in the intersection of two submodules, so in the intersection of L1 and L2?
Why this intersection is not 0?
Exactly, because if I take X, I have this property with P1 and P2, and P1 and P2 are different. So this can be true unless X is equal to 0. So this actually is 0 submodule. But that's a contradiction, because you see the module N, which is a 0 module, in these cases it can be actually presented as an intersection of two submodules. So let me say that there are no X's here which are not equal to 0. So hence this intersection is 0. Hence 0 module is the intersection of L1 and L2. So that's a contradiction. Okay, corollary, which has a special name, Laskan theorem. So this special case for ideals is called Laskan theorem, and it says the following: if you take ideal I in an Noetherian ring, so in Noetherian R, so then this I can be presented as a finite intersection of Q1 up to Qk, where Qi are primary and radicals of Qi are distinct prime ideals. Uh-huh.
So such that all pi are distinct.
Mm-hmm.
Okay, but we not removed it from representation.
No, we can't remove them from representation in general.
So not for any n we have shortest decomposition.
No, we always have shortest, exactly by this process of grouping.
Well, shortest is when they grouped, not when they won, only one.
Well, when we group them and then we intersect them, you still get prime.
Yeah, yeah.
Oh, group and we like group and say that this one model.
Yeah, so when you're grouping, you just essentially you keep the same intersection, the same module. For example, n1 and n2 has the same associated primes. So instead of n1 and n2, you consider new modules and n1, 2. Right, so the intersection of n1 and n2. So
It's reducible.
Yeah, but shortest is in a sense the opposite of irreducible decomposition.
why?
Well, because in irreducible, every submodule can be represented as an intersection. And here we group them and take them intersections, therefore they're reducible. By the way we...
Well, that depends. Do you need to group or not? Well,
Yeah, but even...
Yes.
a priori you don't know. Maybe all irreducible. Well, you don't. Maybe you don't need to do any grouping. Maybe they already have distinct prime ideals. So the idea is you can start with any irreducible decomposition, right? Then perhaps you need to do some grouping, and then you get the shortest. Well,
Yes,
so you get shortest primary decomposition.
yeah, but if you like have n1 and n2 have same pi,
Mm-hmm.
yeah, you group them
Mm-hmm.
and like you get some n0.
Mm-hmm.
That's intersection of n1 and n2.
Mhm.
This is not a primary ideal. Or is it?
This is not irreducible ideal, irreducible submodule, but this is primary, still P primary. So by grouping, you losing the fact that this is decomposition, irreducible decomposition, but you're obtaining the fact that this is shortest primary decomposition.
Why we need a redundant decomposition?
Well, because if you have a decomposition which is not irredundant, you can just remove some parts and get an irredundant.
So we constructed a redundant primary decomposition.
Yes. Yes. Yeah. So all our decompositions will be irredundant because otherwise we can construct an irredundant decomposition. Yeah, I just want to make a brief remark about the last statement. So the last statement, if you think about this geometrically, it says the following. If you consider corresponding variety, so V of I, then this is a union, well, maybe I keep this, V of the Q1, V of the Qk, right? But when we consider V, well, we can go to the radical. So if I go from the radical of the ideal, from the ideal to the radical of the ideal, V stays the same. So here, Pi is the radical of the Qi. So geometrically, what we've done, we consider the corresponding variety and present this variety as the union of the distinct irreducible components.
Okay, you use the name variety. What is it?
V of I by definition is variety.
Okay.
So this is what I call variety in this course. V of some ideal.
Like Don't we call this something like vanishing line?
Well, yeah. So this is also the closed subset where elements of the I is vanishing. Yeah. So vanishing subset or variety of the ideal. So the meaning of this last theorem is that we can geometrically take any variety and express this variety as a finite union of irreducible varieties, where all these components are distinct. So, and this is because the terminology from varieties, that this is our irreducible varieties, give us terminology for ideals, and not for ideals, but for decomposition. And people notice that can be generalized for modules, not just ideals. So originally, in the papers of Laskan and Noether, this was developed only for ideals. So Laskan and Noether was the first theorem proved in this direction. And then later, maybe 10 years, 20 years later, people realized that the same arguments can be simplified and used for submodules. Okay. So now let's do a couple of examples. So first is quite natural. So you take a principal ideal generated by the n inside the integers. So then clearly you have a decomposition like this. You have p1 to the n1, intersection with pk n to the k. So pk to the nk. So where this n is just the product over powers of prime numbers, right? So then in this case for Z, or more generally for principal ideal domains, these decompositions that we proved in general for any Noetherian ring, it just corresponds to decomposition of the generator of the ideal into the product of irreducible elements, powers of irreducible elements. So in this sense, this if you kind of like results like this for about unique factorizations, if you want to generalize this, the most general statement for Noetherian rings is kind of this statement. Okay. Example 2 will be not really an example, but an exercise. So here we consider polynomial ring in two variables and consider ideal generated by the y squared xy, two generators. So then I claim that I can intersect this as y. So I can obtain this as intersection of the y and the xy squared. Or I can do this as an intersection of the y intersect with the x, only y squared. And also I can get this as an intersection of the ideal generated by y and ideal generated by the y squared x plus y. And finally, intersection of y and y squared xy x to the n. N is any number which is greater than 0. So why I'm showing you this example? Well, there is a quite natural question. This shortest or minimal irreducible decomposition, is it unique? Well, it's very far from being unique. So as this example indicates. But we have actually some uniqueness results, some partial uniqueness results. So for example, we have this decomposition. So this gives us some set of prime ideals, right, which are associated if we have ni's, and M modulo ni has only unique associated prime. So for any I, we have a unique prime ideal. So we have this family of prime ideals. So the question is how this is related to the set of associated primes that we introduced before. And the answer is the following proposition. So if we assume that n is the intersection of ni's, such that associated primes of the M modulo Ni is exactly Pi. So this is irredundant primary decomposition. So then I have two observations. So first observation is that the set of the associated primes M modulo N is the same as this set of primes that we obtained this way, as the associate primes of the quotients by individual modules. And moreover, we have the second part that's saying that the set of the associated primes of the Nj modulo N is the same as the set of the same prime ideals as before, but you need to remove one prime ideal with the index j. So this is for any j between 1 and k. So we can think about this as a first kind of uniqueness result. The prime ideals that we see for the primary decomposition, they are actually the same prime ideals that we see in the associated primes. Okay. So first, let's prove the first part. Again, as before, without loss of generality, I can go to the quotient, and I can only consider the case when the modulo n is equal to 0. Okay, so then I can say that M is a submodule in the direct sum of the quotients M modulo Ni. Right, so in general, I can embed M modulo N in this direct sum, but since N is 0, I can embed M. And then by the basic properties of the associated primes, I can conclude that the associated primes of the M are contained in the set of the associated primes that we are given. Right, so associated primes here, it will be just the union of these sets. So this gives us inclusion in one direction, in the first property. Now let's do the inclusion in the other direction. So since we know that the decomposition is irredundant, I can say that if I take the intersection over all I not equal to j of the ni's, then this module is not equal to 0. And so being irredundant gives me this property. So this is for any j. So then I take this non-zero module and I can do the following trick. I can keep this intersection, but then I take quotient by the same intersection, and I also intersect this with Nj. So this is the same thing. Yeah, so this intersection is exactly the intersection that gives me n, but n is 0. So this is the same thing. Now to this intersection, to this quotient, I want to apply the Isomorphism Theorem. So and then this tells me that this is the intersection over I not equal to j, and I plus nj. And then I need to take a quotient by the nj. But at least for this quotient, I can conclude that this belongs to this quotient modulo M modulo Nj. Okay, so now what I can say that this module, so this is a non-zero module, so it has non-empty set of the associated primes, and this set of the associated primes has to be inside this set of the associated primes. But this last set of the associated primes has only one element. So associated primes of the intersection I not equal to j of the Ni is precisely Pj. Right?
How are we going to say that this associates with intersection plus nj?
Hmm? No, I'm saying that this is non-zero module, so it has a non-empty set of associated, and this non-empty set is contained in the associate primes of this set, which is just one element. So it means that these two sets has to coincide. So that was the argument. But now notice that this intersection is a submodule inside given module M. And if some associated prime is associated with the submodule, it is associated with the module. So it means that all these prime ideals are associated with the M. So hence, P1 up to Pk, this is a subset in the associated primes of the M. And this finishes the proof of the first part. Okay. In the second part, I'm not going to assume that n is equal to 0. Well, I consider canonical map from nj to the sum, so sum over I not equal to j, so this is nj modulo Ni intersect with nj. Okay, so let's take this map and let's try to understand the kernel of this map. So let's call this phi. So what's the kernel of phi? Well, the kernel of phi, well, I claim that this has to be precisely the intersection of the I not equal to j of all ni's, right? And also I need to intersect this thing with the nj. Okay, but this is exactly n. So the kernel of this map is exactly n. So in other words, nj modulo n can be embedded into this direct sum. But then again, I look at the associated primes. I can say that the associated primes of the nj modulo n is a subset inside the union over I not equal to j of the associated primes of the nj modulo Ni intersect with nj. Okay, so now let's look at this last module. So nj intersect quotient by the Ni intersect with nj. Well, again, let's use the isomorphism theorem and see that this is the same thing as Ni plus nj quotient modulo Ni. And this sits inside M modulo Ni. But I claim that I already kind of proved the second statement in one direction. I have one inclusion. If I have this inclusion, so this module sits inside this module, again as before, associated primes of this quotient is precisely Ni. So exactly precisely Pi. So, and here I have all Pi's where I is not equal to j. So it means that the associate primes of this is exactly subset here. So hence we have associated primes of the nj modulo n. So this is subset in the Okay, so to finish the proof, we only need to show that there is inclusion in the other direction. Okay, to do this, we need to notice that there is a short exact sequence, which is just a form of the isomorphism theorem. So nj modulo n is mapped to the n modulo n, and this is mapped to the m modulo nj. Okay, so then this gives us that the associated primes of the term in the middle sits inside the union of the associated primes of this quotient, which is just pj, union with the associated primes of the nj modulo n. Okay, but I think that's enough to show that we have inclusion in the other direction. So here we have this, by the property 1, we have this list of prime ideals. And this list of prime ideals has to be contained inside this ideal Pj and the other ideals here. But it means that ideals here has to contain everything except maybe Pj. So it means that we have inclusion here in the other direction. So this set belongs to this set. Okay. So this is the end of today's lecture.